Okay, so hi everyone. My name is Chien-Chin, and this is Xilun. We are from PyTorch distributed team. Today we are going to talk about how we combine FlexAttention, which in the previous talk just described, and combine FlexAttention with context parallel. So if you are not familiar with FlexAttention, or like you just heard the FlexAttention from the previous talk, and then you can take a rest for 1 minute. Otherwise, I'm going to do a quick recap of FlexAttention. So PyTorch FlexAttention is a flexible API that allows users to pass in optional score mode or mass function to customize the attention behavior. So the key takeaway for this slide is these two functions actually take in the QKV indexes as the input to customize the score or to decide whether this QKV pair are going to be computed or not. In other words, masked. And the next one is a context parallel. Context parallel is one type of data parallelism which divide the sequence into subsequence. And then we can compute, do all the compute like embedding or a memo without any communication in the forward. However, when we need to do attention operations such as FlexAttention, we need to do an OR getter to gather the full KV information, or we can use ring attention to overlap the communication with computation. At this moment, we only have an OR getter version and still working on the ring attention version for FlexCP. So why is it so special FlexAttention and combine it with context parallel? So one key factor is, again, the block mask. Block mask, it contains the sequence information and also mass function. So we cannot simply divide it or shard it along the sequence dimension, just like any other input, which we just shard the sequence dimension along the sequence dimension. So block mask can be a trouble when we try to apply context parallel. But in the meantime, block mask also gives us the sparsity information, which means that the QKV pair, which are masked over the all QKV pair. So higher sparsity means that the lower computation. So this is one information we need to utilize when we do context parallel. So let's talk about how are we going to solve the issue. So we introduce a context parallel shard, which takes in the input data like input tensor or label, but it also takes in the block mask. When the API detects the input are tensor, it will simply shard this tensor along the sequence dimension. But if it detects the input is actually a block mask, it will first, again, shard along the sequence dimension, but it will also rewrite the max function based on the provided device mesh information, which tells us the context parallel information. And we will rewrite such that the local QKV indexes will map back to the global QKV indexes. And we can also notice that there's a low balance argument for this context parallel shard API, which will be very useful for the next topic. Okay, so next, Xilun is going to talk about how we can utilize the sparsity information.
Thanks, Chien-Chin. So we did a small benchmark on FlexAttention with masks of different density. And we found that the forward and backward time is proportional to the density. So that means in context parallel, if we shard QKV tensors in an unbalanced way, the computation distribution will be uneven, leading to straggler. So the goal of load balance is to minimize the highest density on rank. One way to achieve this is to reorder the QKV tensors before sharding. And how we reorder them can be modeled as a multi-way number partitioning problem. So let's take a look. Head-tail load balance is a commonly used load balance strategy to balance the causal masking. So if we don't do load balance, you see the density distribution is very uneven. So what it does is, it first splits the Q indices into 2 times CP size chunks. Here we use CP size 4. And it combines Q0, which has the lowest density, with Q7, which has the highest density, and assigned to GPU 0, and it combines Q1, Q6 for GPU 1, and so on. So this leads to a perfect even density distribution. However, static heuristics such as head-tail may not always perform well because they assume a certain density pattern in the mask. So, so therefore, we want to. So if you apply head-tail to this document causal mask, the performance will be bad, and therefore we provide an automatic load balance which can analyze the mask density and generate a load balancing plan based on it. So we will use document causal for the further discussion. We call our new approach process time round robin, PTRR, because we sort Q indices based on its process time, and we assign the Q index to each GPU devices in round robin order. So the first step is to calculate the row density for each Q index. For FlexAttention, this information is pre-computed and stored in block mask. And once we sort Q index based by the density, we select in the round robin stage, we select the first 4 Q indices with the lowest density and assign to GPU 0, 1, 2, 3. And in the next iteration, we select the next 4, but assign to GPU 3, 2, 1, and 0. So we keep iterating in this zigzag order, and this will give us a much more even density distribution. We also benchmarked and compared the performance of these 2 strategies. We use Torch Titan llama model training with document mask on varying document size. We set sequence length to 128K. So the first benchmark uses small documents. Most documents in C4 English dataset have length below 4,000. So the mask density in this case will be very small. It's only 2%. And we see head-tail shows a very small perf regression because the load balance step has a computation overhead. And most importantly, the actual density is very different from the assumption that head-tail makes. However, PTR still shows a positive perf gain here. And the next benchmark uses medium to large document. So we synthesize the data set from C4 by merging every 100 documents. So this amplifies the document size by 100 times and increases the density from 2% to 15%. And we see both are showing positive perf gain. And the PTR shows a significant more than 20% perf gain in this case. In the last benchmark, we switched from document causal to causal mask. This means the whole 128K sequence will belong to the same document. And both are showing more than 50% perf gain because of the extreme computation imbalance in causal mask. And we also want to share some planned works. So in the short-term goal is to reduce the load balance algorithm overhead. So potential solutions include, Sorry, we're running out of time. And so potential solutions include, can we have 1 more minute? For example, we can use touch.compile to speed up, and we can offload the load balance algorithm to CPU. We can also move load balance to the data loading stage. The long-term goal would be adding ring attention and a sparsity-aware communication. And the APIs are already in the PyTorch nightly, so you can try it on your own. And thank you for coming to our talk.